Hi, now we have homeworks on 1.6, but the second part on quantified statements. So I told you to do number 14a and d. So let's look at these statements. And so it's always the same thing. We have statements, English statements. So Linda, a student in this class, owns a red convertible. Everyone who owns a red convertible has gotten at least one speeding ticket. Therefore, that's what you have to prove, someone in this class has gotten a speeding ticket. So, first thing to do is decide on, let's call that step one, decide on the predicates that you're going to use. Because as we quantify, we need predicates, right? So the first, Linda, a student in this class. So let's say dx is the statement x is a student in the class. I'm using D for discrete math, in case you wonder why I choose a D. I don't know, I did that in the other video as well. Owns a red convertible, so Rx is a red X is a red convertible. I think this is a question in made for students in a different kind of school. I don't think that many people in New York have a red convertible. It's also perhaps not the best thing to have in New York City. And then everyone who owns a red convertible has gotten at least one speeding ticket. Let's call that S of X. X has gotten a speeding ticket. So step two, what is the information that we have? Linda, a student in this class, owns a convertible. Now let's think about what actually we have here. We have information about Linda, and actually we have two statements about her, namely that she's a student in the class, so this becomes D Linda. There's nothing else to say about that, right? It's just Linda is a student in the class, and she owns a red convertible. So again, it is really just an instance of that predicate. But we have also a real quantified statement. Everyone who owns a red convertible has gotten at least one speed ticket. So, one more time. English has many ways of saying quantifying, and everyone, every, all, any are clearly universal quantifiers. And the best thing to explore what it actually is to formulate a sentence in your own words, in a different way. What it says, everyone who owns a red convertible has gotten at least one speeding ticket. It says that, well, if you own a red convertible, yeah, then you have gotten at least one speeding ticket. So, an if then. So, for all x, because it's a universal statement, if you own a red convertible, then you have gotten a speeding ticket. And then last step, well, not last step, but setup. This is actually only just a setup. I haven't done anything yet, but it's a setup. So in the last is what is it that we want? And namely, there is someone in this class has gotten a speeding ticket. So there is an x, dx, and sx. Why not an implication, you might say? Well, let's see. If I would put an implication that says there is a person that if he is in this class, then he has gotten a speeding ticket. That is weaker than saying there is someone in this class who has gotten a speeding ticket. So it is not conditional, it is really somebody in this class. So okay, it's subtle, right? In English, it's the sentences all think the same, but if you're really gonna unravel what they say, they are represented differently in formal language, and that's also the reason why reasoning in English, in other words, in our daily language, is less accurate, because we have this kind of vague interpretation of what these things mean. Whereas as now, once we do what we can now do is we can ignore this part. Whatever this means, the only thing that we have is this information. And from this information, we're gonna logically from this information, we're gonna get to this truth. No matter what DRR all this stands for and who Linda is. Okay, so let's start. So if you want now the step 4, right? Now in step 4, the actual proof. So this is the, let me call it, that's the proof that we're going to give. I kind of want to keep my eye on the price here. And getting an eye on the price tells me I need to find something about D. There is an X. What does that mean? By now, if you remember, you will see again this. We're gonna at the very end of it, we're gonna do existential generalization. In other words, what we're really looking for is a person that is in this class and satisfies this thing, has a speeding ticket. But let me now make it abstract and don't anymore say what D and S stand for. Just say what we want is something that satisfies D and something satisfies S. Now, we do have something satisfying D. We also even have something satisfying R, but we don't have anything satisfying S. So we're missing information. So we need something about S, but the only other thing the only place where S is mentioned is in the third statement that we have. And so it's clear that to get this, we need this. And we kind of have that. So I think our strategy is clear. Let's now make it correct. So the first thing what we want to do is using somehow, as you noticed in this thing, and you'll see in the other exercises and the quiz review for the next quiz. The next quiz will be something like this. Is that we want to get rid of our quantifiers, because quantifiers again is something very hard to deal with. Once you have a quantifier, it kind of closes up everything that follows. So you want to get it, you have to pass through this quantifier first, and what we do is the so-called, so let me copy, so I have this statement, and so what I'm going to use is universal instantiation. That means we're going to give an instance for X, and since it's a universal, we can choose whatever X we want, and so in this case we're going to take X to be Linda. So this then says that if R Linda, then S Linda. And here Linda could be anything. Okay, it's the name of a person, but the whole point is that we don't need to know what R and S are. Okay, now we're getting anywhere because we do have R Linda. We know also this fact that's given to us. So from this we can get, by what we call the regular modus ponens that we discussed last time, we get S of Linda. If the hypothesis holds and you have the implication is true, then the conclusion is true. Good. So what we have actually D, R, and S. The only predicates that we have, they all satisfy this Linda. Where we want is D and S. So we kind of have to combine the facts that we know about Linda, the S and D facts. And that is S Linda and D Linda. And this is what we call conjunction. If you have two true statements, we can make it into a single true statement by just conjunction, by ending, sorry. I mean to say by putting and in between. And then we are there, right? Because I did the kind of silly thing. I put them in the wrong order for what I want, so I'm going to put them in the right order so that it looks nicer. And that is okay, because we know that the order in which we take an end is not important. Okay, so what we're going to do? Well, we have a Linda, that's a witness, and so this is now the rule of existential generalization. Instantiation means that you give a value for X. Generalization is that you have a specific thing and you make that to an X plus a quantifier. In this case, existential, so we have an existential quantifier, so we're gonna have, there is an X, we replace Linda by this X, the X and SX. That's how the formalism works, right? It's all, when we say formal, perhaps what I really mean by that, it's machine formal. A machine, a computer program, knows how to do all these steps. It doesn't know what R and S are, and even if we tell them what R and S is, it doesn't mean anything unless we have a artificial intelligent computer, which we at this point not really have yet. Okay, so that's 14a. Let's move on to 14d. Right, that's what the other one. Sorry, yeah, 14d. 14d says there's someone in this class who has been to France. So again, I'm going to already start with our thing. dx is still x is in a class. There's someone in this class who has been to France. So let's call f of x. Now this time x has been to France, has visited France. Okay, and then everyone who goes to France visits the Louvre, Lx. The Louvre, if you don't know what that is a famous, it is now a museum, but it used to be the royal palace, and it's a huge royal palace. It's probably the biggest palace, royal palace in the world. X has visited the Louvre. Louvre. No, sorry. No, I don't know how to write Louvre. It's with a U, right? Right, of course, it's with a U. The Louvre. Okay, so that's the step one. And there's some conclusion that we have to draw, but I have decided my predicates are, let's go to each of the sentences. Perhaps I forgot the predicate, so I will add it. So, the first sentence is, there is someone in this class, clearly we are dealing with an existential statement, who has been to France. Again, no implication here, but if you really think about it means there is somebody, that means there is somebody who is in this class and to France. Is it an implication? Does it mean that if you were in this class you had gone to France? No, I'm not saying that. I'm just saying there was somebody in this class and that same person also went to France. So we have dx and lx. The second statement says everyone who goes to France visits the Louvre. That's clearly a universal, everyone, all, for all. Who goes to France visits the Louvre. Let's reformulate it. If you go to France, then you go to visit the Louvre. So it becomes clearly an implication. So f of x... Oh, sorry. I got confused with... my first statement was there is someone in this class who has been to France. So that was f, not l. Okay, sorry about that. I got my letters confused. And so now the second statement is everyone who goes to France visits the Louvre. This is fx implies lx. And so to show, step 3, that someone in this class has visited the Louvre. There is an x, that person is in this class and has visited the Louvre. Again, no implication here. It's just two facts about this same person. And okay, let's go quickly, right? We have two quantifiers. We want to get rid of them. The first one is an existential. That is existential generalization, instantiation. The second one is universal instantiation. So which one to do first? Well, this is not, it's not 100% carved in stone rule, but almost always you do first existentials because the existentials give you no freedom. There is somebody, but that might only be out of the 10,000 possibilities, only one that perhaps works. You don't know. So you have to, when you take an existential instantiation, there's only one fixed thing. Whereas if you do a universal instantiation, you can pick this for many choices for x. So existential somehow is the one that we should resolve first. So there is an x, dx, and fx by universal instantiation, existential instantiation. We have dA and fa for some student A. But that's all we know, that there is a student and we have called that student A. The student has a different name, but we don't know that name, so we have to call him student A. We don't want to call him student X because X is now reserved for variables. So we like to use a different letter. Good. dA and fa. So what we want. What we need, let's go again, we need something about an existential. So we need, in other words, we need a witness for D. We have a witness for D. We have a witness for F. We don't have a witness for L. Well, again, we have this universal rule here. So by universal general instantiation, universal instantiation. That means, but this the freedom I have with universal instantiation is that I can take for x whatever I want, and I know what I want. I want to take this guy here, A, whoever that is, but I want that. Okay, so we have FA implies LA. Remember, instantiation means you erase the quantifier and you replace x by A, wherever x is. Good, so what we want, all right, so we should also, now from this FA I can LA. Do I have FA? Well, I have this DA and F here, here. So I should perhaps from that get, what do we need? F of A. So remember, this is the rule called simplification, I think, but it's kind of an obvious rule. Yep, okay. But technically there's a step to be done here, right? We have DA and FA, but from that we know FA follows from that. These two things have to be true, so at least either each separately has to be true. So also DA is true. Perhaps why not? Let's also conclude that now, because you'll see we'll need it actually later. Now that I have FA, I have also, this one is now also a truth, right? This is one of the things that I established. So using, okay, of course, obviously I'm using these guys here, right? Using these two statements, I can use a modus ponens to conclude LA. So I'm getting close to what I want, right? This is what I want. And I have DA and LA, so now I have to put all this together. So let me copy this guy here. I have DA, and therefore LA and DA. This is what we call conjunction. And then finally, this is, A is a witness, and we can now use universal, existential generalization. Say, okay, there is an X, Lx and dx, as we needed to prove. Okay, and so then that was for 1.6, right? Yes, for this was, yeah, I said that, right? 1.6 here, but there, I also gave you something from 1.7. You have more homeworks this time, but so let's see, what one was that? 1.7. That was number 10, and that said use a direct proof. We at this point only explain direct proof, so you can ignore what this direct proof is, to show that every odd so that the product of two rational numbers is rational. Now I also told you go to definition 2 on page 85, because I hadn't talked about this, so I just want to make sure that you know exactly how to use this. Well, I think everybody knows what a rational number is, I hope. It means a fraction. But what is it? A good definition, so for rat x, so here x is now over the real numbers. Okay. We are sometimes very lax in saying what x is. Like also here, when we make the statements of x student in the class, x is, what do we mean? X ranges over what? Or all the students in the school, or all people on earth? Yeah, okay, at this point it sometimes it doesn't make a difference what the domain is. Sometimes it does. Here it is important that we know that the domain is real numbers, and for instance not the integers, because there are very few integers that are fractions. No, that's not true. Every integer is a fraction, but that's not there are very few fractions that are integers. I said it wrong. Okay, so what does rat x mean? Rat x means that your fraction, but let's make this into a statement. There are P and Q, so that that Q is not 0 and X is P divided by Q. That is what to be rational. Notice that this extra little condition here, because I'm not allowed to divide by 0. So it is actually an existential quantification. Notice that I use P and Q here as variables. Okay, once I write down an existential quantifier, I have no more choice. P and Q are now variables and not propositions. That might be something that's kind of weird, that we were using P and Q for propositions. Well, this tells me here P and Q are real numbers because I'm quantifying over them and the domain are the real numbers. If you don't like that, use Y and Z. But, so, okay. So that is red X. And so what does the statement now say? What we need to prove is if red X and red Y, oh, sorry, that was, let me get rid of this. Red X and red Y, then red XY. Okay, so let me read it again. That the product of two rational numbers is rational. Now again, you say there's no if-then. Well, it is implied, right? It says that if x is a rational number and y is a rational number, then x times y is a rational number. So that is what the statement says. Now, how can this be true? Because it's a predicate. There are variables in it. And this is what we discussed in the lecture last time. Very often, when we say that this is true, we mean it's true for all x and y. So we have an implicit universal quantification. Good. Now the proof, that how do you prove this? This is of course what we want to do, is we use somehow the universal instantiation. So we say let m and n be rational numbers. In other words, that means ret of m holds and ret of n holds. A direct proof, that's the only proof I so far have discussed, of implication is you assume that the hypothesis is true and the only thing you have to show now is the conclusion. Okay. Now ret m is this, formally it's this statement, so I can unravel the definition here if you want, and what the correct way to say is that I'm doing an existential instantiation of this existential quantifier, well, double quantifier. There is a P and Q, so it means there are P and Q with Q non-zero. I'm going to make it a little bit smaller, shorter than that. M is equal to P divided by Q. That's what it means for M to be rational. Now, what it means for N to be rational? Well, there are, and here is a very common mistake, to say P and Q such that da da da. But I have used P and Q. Now remember, I'm doing this from here to there. Technically, officially, if you want, formally, what happens is an existential instantiation. I'm going to do another existential instantiation. There is absolutely no guarantee that this existential instantiation gives me the same witnesses. So I cannot use the same names. So the formal reason for that is because I'm doing two different instantiations, and therefore I have no prior knowledge that they will be both the same. So I cannot assume that, so I have to give different names for that. There are S and T, with T not zero, such that N is S divided by T. And that, as I said, a very common mistake is to use the same P and Q here. Now, so far I have set everything up, but now I have to start thinking about what I have to prove something about x, y. Well, about this term, so to show, sorry, I should set that here. So I am assuming ret m, and so what I have to show is now ret of m times n, right? The whole trick here is that we know a little bit more about m and n than originally. Originally were just two numbers. Now we know that they're allowed to form P divided by Q and S divided by T. Where, sorry, I should have said this, where there are P and Q, and here the domain is integers. So that's perhaps something I should have specified that, because that's the whole point, right? That is that we can write a fraction as a well, that we can write a rational number as a fraction of integers. So P and Q, there are integers, P and Q here, and that's the same thing here. That's another thing, right? Each variable, and therefore each quantifier that uses that variable, has its own domain. So here the P and Q are round of the integers, x and y are real numbers. Okay, so we have m is p over q, n is s over t. We need to know something about m, n. Well, we have some form. Let's work it out. pq times st. Now, how do you multiply Rational numbers, well, that's very simple. You multiply the numerators and you multiply the denominators. And what we need is, do we have to verify this existential quantifier? Are there two, but now be careful, right? Don't read this as actual p's and q's, read this as variables. Are there two integers so that I can write the number that I'm interested in as one over the other? And moreover, the bottom one is not 0. Well, yes, this is an integer, this is an integer, getting very close. It's a fraction. Is this non-zero? Yeah, and qt is non-zero. Why is that? Because of the zero product property. Remember, that says if you have two numbers that are non-zero, then their product is also non-zero. Oh, the contrapositive, by the way, of this statement is that if, no, that's not really, if two numbers, then they're both, yeah, right. So the contrapositive is that if, sorry, that's not what I want to say, sorry. Okay, sorry, I was going on tangent, I shouldn't have done that. Okay, so what this means is this is now by existential generalization, but I'm putting in parentheses because in proofs like this it's almost, we feel that this is what we're doing. It's like everybody understands this. Everybody that is used to mathematics knows that this is what is going on. So we say, this shows me that ret mn, because mn is written in as the definition of what a rational number is. Okay, so that's for number 10. But we're going to do much more on proofs. If you heard what we do, these more strange proofs, and those are more the ones that I want to quiz you on.